organizers for giving me this opportunity to present our research activities at this nice conference. Unfortunately, I cannot participate in person due to the COVID situation. I hope I can visit Turkey in a future ICSM conference. Okay, the title of my talk is Unique Superconducting Properties of 144 materials, and collaborators, those people and people in PUVIN who supported the magnetization measurement and analysis, and the people in NIMS who conducted beautiful STEM observations, and the people in CROSS conducting neutron scattering measurements, and the people in Japan who supported the sample preparation. Today, I'd like to talk about two topics on 1144 type materials. The first one is the advantageous vortex spinning properties in calcium potassium 1144 arising from unique defect structure revealed by microstructure observations. Secondly, I would like to show you the unique historic behavior of European moments induced by vortices in the magnetic superconductor Europium rubidium 1144. Here, I also would like to talk about the possibility of the manipulation of spin domain structure using vortices in this Europium rubidium 1144. Okay, let's move on to the first topic. There are already nice introduction about iron superconductors in the previous talks. So here, let me briefly introduce the characteristics of 1144 type materials. The crystal structure of 1144 is very similar to the well-known 122 structure. However, different from 122 type, where alkaline and alkaline earth elements occupy the same site. In 1144 type, alkaline metal and alkaline earth layers stack alternately. So this is say line compound. And like the 122 materials, 1144 materials are characterized by high transition temperature and large apocritical fields and small anisotropy, which makes them attractive in terms of high field applications. In addition, because the chemical composition is fixed to 1144, homogeneous properties are expected compared with 122 type. Moreover, it has been reported that calcium potassium 1144 shows extremely high JC values with a large anisotropy against magnetic field. Also, when you see the temperature dependence of JC, you can see that once JC goes down with increased temperature, but it slightly increases with increased temperature. So this is, say, a kind of peak effect in temperature dependence. So these JC properties are distinct from total 122 type. Revealing the origin of these unique JC properties is very important for applications as well as vortex physics. So motivated by these results, we investigate the microstructure of calcium potassium 144 single crystals. And single crystals of calcium potassium 1144 were grown by the iron arsenic flux method following the Meyer's work. And the grown crystal like this, and a sharp superconducting transition was observed by the magnetization measurement, and the implant resistivity showed a high residual resistivity ratio, around 16, which indicates the high quality of those single crystals. And the XR pattern only shows 00 error peaks of calcium potassium 1144, namely, there are no trace of 122 phases. However, you can see that the 00 error peaks at higher angles are rather broad, and such feature can be also seen in the previous works. So although crystal quality seems good, but the 00 error peaks are rather broad, such feature This may indicate that some presence of defects such as integrals, which cause the peak broadening. Then we performed the scanning transmission electron microscopy on the calcium potassium 144 single crystal. This is a low magnification image. Here, characteristic bright stripes in the horizontal direction with typical length about 1 micrometer can be identified. And this is a magnified view around one of the defects. And the high resolution image of the matrix part reveals a bright zigzag corresponding to the iron arsenic layer and relatively dark layers with different layer distance corresponding to calcium layer and the potassium layer respectively, which are in good agreement with the crystal structure of calcium potassium 1144. Then when the bright stripe defect is magnified, we found that the zigzag structure, namely iron arsenic layer, is maintained, while the alternation of calcium and potassium layers is violated. Here, the thickness of the defect is about 55 angstrom, which is 9 times of the calcium iron interlayer spacing sandwiching calcium layer. So this defect likely to correspond to the 5-unit cell calcium 122. Furthermore, by carefully investigating the microstructure, we found much thinner defects, which are identified to be the monolayer calcium 122. And chemical composition analysis also supports that these different defects are calcium 122 integrals. So here calcium is rich and here potassium is poor. So such integrals are unique 1144 type, where alkaline metal and alkaline earth elements do not occupy the same site. So these defects possibly give rise to the unusual JC properties of 1144 materials. So here let me discuss the nature of these defects. And in the case of the thick integrals with thickness much longer than the coherence of 1144, because calcium 122 is the non-superconducting parent phase, these are probably normal defects and expected to act as spinning centers. On the other hand, in the case of thin monolayer integrals, holes are expected to be supplied from potassium layer, although it is a bit away from this iron arsenic layer. And comparing the phase diagram of 122 material, although the hole concentration should be depleted compared with 1144 matrix, so maybe around here, the monolayer calcium 122 is probably superconducting, and the TC of the defect is expected to be lower than TC of defect, TC of the 1144 matrix. Then let me discuss how these defects correlate with JC properties. As we observe, there are two types of defects in calcium potassium 1144 single crystal. One is thick and large integrals, which are considered to be normal planar defects. These defects are in general very efficient to pin centers and the magnetic field parallel to this plane. So in this case, AB plane. On the other hand, they are not efficient for the field perpendicular to the plane, namely along C-axis. Therefore, we consider that these defects are responsible for the extremely large JC with field along the AB plane and the resultant of large anisotropy against the magnetic field direction. Then for the other one, the thin and small integrals, they are thought to be efficient for both magnetic field along AB plane and C-axis. Meanwhile, when these defects become superconducting by lowering temperature, we expect that spinning also become less efficient. This possibly causes I hear some howling.
Could you mute?
Okay. Okay.
Okay. Thank you very much.
Okay. So this small thin and small integrals is superconducting at low temperatures. Maybe the defects become less effective at spin centers. So we expect these kind of defects are responsible for the peak effect. So increase in JC with increasing temperature observed in the this calcium potassium 1144 material. Okay, finally, in the first part of let me briefly introduce the recent reports on microstructure and JC properties in calcium potassium 1144. We first observed calcium 122 integrals, while it has been revealed that potassium 122 integrals also exist in this material. Potassium 122 integrals are thought to be Hall-rich, and they can be superconducting or normal defects depending on thickness and temperature. As in the case of calcium 122, they are also expected to act as efficient spin sensors. Regarding the JC properties, it will demonstrate that JC significantly depends on the sample thickness. So by making the sample thinner and thinner, JC goes up by a factor of 10 or more. Additionally, a comparison between single crystal with different defect structure showed that dominant spinning mechanism is different for crystals with calcium 122 and potassium 122 integrals. So these JC properties are very interesting, and that's one of four type materials iron-based superconductors not only attractive as in terms of application, but also very interesting target to study vortex physics. Okay, then let's move on to the second topic about magnetic superconductor europium rubidium 1144. Magnetic superconductors where superconductivity and magnetic coexist are unique targets to seek for novel phenomena. And recently, iron-based superconductors containing europium have attracted much attention as a new family of magnetic superconductors. Compared with known magnetic superconductors, europium-based IBS are characterized by high TC and HC2 and possibly high JC. In fact, there are various observations of novel phenomena such as reentrant superconductivity and spontaneous vortex state and so on in the europium-based iron nickel materials. And in this study, we focus on europium rubidium 1144. Europium rubidium 1144 showed the highest TC around 36K and high HC2 around 70 to 80 Tesla, which are highest among the europium-based IBS. In addition, a neutron diffraction study revealed that europium moments align ferromagnetically in AB plane, and the orientation rotates by 90 degrees in the next layer. Namely, the ground state is helical like this. Here we expect that high TC and HC2 probably lead to high JC, which creates strong internal fields due to the spin vortices. And sorry. Note that the magnetization field measurement suggests that the European movements are easily reoriented by magnetic field. So you can see the saturational moment indicating the ferromagnetic alignment of European moment in magnetic field. Then we came up with an idea that if vortex spinning is strong and creates strong internal field, European moment would feel the internal field and follow the direction of pin vortices as illustrated here. Motivated by this idea, we grew single crystals of European rubidium 1044 using rubidium arsenide flux method following the Bow's work, and we obtained millimeter-sized single crystals. Magnetization shows a sharp superconducting transition and the kink feature corresponding to the magnetic ordering of European moment. XR pattern shows no trace of 1 to 2 phases, and using this high-quality single crystals, we perform neutron diffraction measurement at the St. J Park. In the previous study, we demonstrate the helical order at the zero magnetic field, while in this work, we applied magnetic field along AB plane. So far, it has been assumed that the magnetic structure of European moment behaves in the reversible manner, as shown here. I mean, by applying magnetic field, it reoriented ferromagnetically, but by turning off magnetic external field, it returned to the original helical structure. So there is no, it is assumed that there is no significant interaction between European moment and vortices. Okay, let me move on to the results. The neutron diffraction patterns and the zero field cooling condition reproduced that the previous report. You can see 00L plus minus 0.25 peaks demonstrates the helical ordering of the European moment. Then, by increasing magnetic field, it is clearly seen that the intensity of 00L plus minus 0.25 peaks gets weaker and vanishes under magnetic field around 0.4 Tesla. This indicates the European moment are reoriented and aligned ferromagnetically along the direction of the magnetic field. This is what we expected from magnetization measurement. On the other hand, when we decrease the magnetic field to 0, we found that the intensity of 00L plus minus 0.25 peaks does not recover. This means that the ferromagnetic alignment is maintained although external field is 0, demonstrating the hysteretic behavior with European moment. The field dependence of 001.25 peak and 001 peak intensity reported in this figure. In the field decreasing branch, the intensity of 001.25 peaks recovers only partially at slightly negative field region, where the ferromagnetic and the helical elements are expected to coexist in the sample. Based on the results, the magnetization coming from European moment can be calculated and showing clear hysteresis like this. Note that the magnetization of European 122, which is the non-superconducting counterpart, shows a negligibly small hysteresis. So therefore, it is expected that the interaction between the European moment and vortices is the origin of this hysteretic behavior. To understand the hysteretic behavior of European moment, we would like to remind how the local moment, local magnetic flux density, B, in the type 2 superconductor varies with external field. So based on the Bean's critical set model. When an external field is applied, the field penetrates to the superconductor from the surface in the form of vortices. Note that the slope here corresponds to Jc, and the smaller b inside the sample results in the negative magnetization. With increasing field, the vortices go inside the sample and fully penetrate to the center of the sample at some magnetic field. With further increasing, this shape of the B profile inside the sample is maintained, and the B goes up. And here, we assume the constant Jc against the magnetic field. So field dependence of Jc is not considered. Then when the magnetic field is decreased, the vortices are removed from the sample surface without changing the B profile around the center of the sample. During this process, the inside the sample gets larger than the external field, then the magnetization becomes positive. With further decreasing field, the B profile is completely turned over. Then, at zero field, there are a finite field inside the sample, and the strength depends on the vortex spinning ability, or Jc of this material. Moreover, at the slightly negative field region, B becomes negative or positive depending on the sample position. Here we assume that the internal B created by the pinned vortices determine the direction of European moment and model it. Then we conducted an experiment to test the possibility of spin manipulation using vortices. As explained in the previous slide, the B profile inside the superconductor depends on the process of application of the magnetic field. Here we consider a process of first decreasing the magnetic field from a large positive field to a slightly negative field, and then increasing the field. Then B distribution in the sample is expected to be shown in this schematic diagram. And based on our model, European moments align ferromagnetically upward or downward depending on the direction of vortices. And the helical order appears around the domain boundaries where the vortex density is close to zero. Then we calculate the field dependence of magnetization. The calculated result becomes like this, with decreasing field and increasing field. And the right figure is the experimental result, which is in good agreement with the experiment calculation results. So the agreement between the calculation and experiment supports that European spin domain structure is successfully controlled by using vortices. And such a spin manipulation may open way to novel device applications such as superconducting memory. Thus, European rubidium 1044 is a very interesting material in terms of basic research and applications. Okay, to summary, for the first part, we observed 1 to 2 integrals unique to 114 materials, which act as effective spin center and give rise to the unusual JC properties, such as the extremely large JC with field around AB plane and the anomalous peak effect in the temperature dependence of JC. And for the second part, we demonstrated the possible spin manipulation using vortices in a magnetic superconductor, European Ruby 1144. And these works are published in this paper. Thank you for your attention.
So then I have questions for the first part. So for your experiment, you observed the calcium 122 integrals, and the quite recent paper showed that the potassium 122 integrals as well. So do you think the both calcium 122 and the potassium 122 integrals coexist in the materials?
Actually, I have no clear idea about the coexistence of calcium 122 and potassium 122 because to my experience, maybe these integrals appear because of some imbalance of chemical composition during the crystal growth. And if locally potassium becomes rich, we observe calcium 122 potassium 122 integral. So if we obtain very, very large crystal and separate them into several pieces and check carefully, we may observe some coexistence of these two kinds of integrals. But if we observe locally, maybe dominated by either calcium 122 or potassium 122.
So the second questions, this is quite interesting on the European Rubidium 1144 systems, and you show us the calculations of the magnetizations and experimental result, and I saw some small differences around the peak of the magnetizations. Do you think this is an artifact? Do you think this is almost the same as the experimental result?
Even this feature?
Yeah.
Okay. I have some additional slide here. Actually, I didn't explain precisely, but we think at some magnetic field, maybe this kind of situation happens where helical paths remained. So up to some field, positive, negative, negative, positive, negative situation, but at some time here, positive, negative, and helical and negative. Maybe this kind of situation is unstable. So we think here is some transition. Actually, in the MH data, we often observe this kind of jump in magnetization loop. So we try to explain this and construct this kind of model. Actually, in the previous one, this feature was not clearly seen, but by changing the condition, we can see this kind of jump also.
Yeah. So we have one question from the online.
Okay.
Professor Evgeny, please.
Hello. Yeah, thank you for nice talk. If we go to slide 3, so I have some question on slide 3. It's
which one? Sorry.
Well, maybe number 7, but yes, 3 is better. So
3.
3.
Sorry.
It's number 3. Yes, so I want to plot on right. Yes, it's this one. So it's the JC were measured by beam model, right?
Mm-hmm. Yes.
So, and the difference is 2 orders of magnitude, right? So, say at low field, I think, or low temperature, it's 15 Tesla. So it's a very huge field, right?
Yes.
So does it mean that? But I think it should be saying the same, right? When we go to saying zero temperature or not. So because it's 100 times, so it's huge, absolutely huge. So
Yes.
so it's 2 orders of magnitude. So it's unbelievable.
Yeah, actually, there is some debate on the magnitude of this value. Actually, this is under 15 Tesla. It's true that we haven't observed such high JC, but at least a recent study revealed that by making the sample very, very thin, somehow JC goes up rapidly. And here, only 0.5 Tesla, but considering the very weak magnetic field dependence of JC, maybe the JC with field along it is playing close to 10 to 8 of ampere per square centimeter.
Right, so this graph is more realistic. So I think that graph is too absolutely huge,
Right.
Thank you for the agreement.
Okay, thank you very much.
Thank you.